Another day, another story. Antimatter is the counterpart to normal matter, with particles that have the same mass but opposite charge. For example, the antimatter equivalent of an electron, negative charge, is a positron, positive charge, and the antimatter counterpart of a proton, positive charge, is an antiproton, negative charge. When matter and antimatter meet, they annihilate each other, releasing energy in the form of gamma rays. Key facts about antimatter. Welcome to Tabo Eminent Channel. Production. Antimatter is naturally produced in some high-energy processes, such as cosmic ray interactions and radioactive decay. Uses. It has potential applications in medical imaging, like PET scans, and even speculative concepts like antimatter propulsion for spacecraft. Storage issues. Since antimatter annihilates upon contact with matter, storing it requires special magnetic traps. Mystery of the universe. One of the biggest questions in physics is why the universe is made mostly of matter rather than equal amounts of matter and antimatter. Antimatter is the most expensive substance on Earth due to the extreme difficulty of producing and storing it. Estimates suggest that 1 gram of antimatter could cost around $62.5 trillion. Production. Antimatter is produced in particle accelerators like CERN, but only in minuscule amounts. It takes 100 billion years of current technology to produce just 1 gram. Storage challenges. Antimatter must be stored in a vacuum and suspended using magnetic fields, Penning traps, because it annihilates upon touching normal matter. Keeping it stable is extremely energy intensive and requires advanced containment systems. Current production rates. CERN produces about 1 nanogram per year of positrons. At this rate, it would take 100 million years to make 1 gram. Uses and future potential medical uses. PET, positron emission tomography. Scanners use small amounts of positrons. Energy production. If we could efficiently harness antimatter, it could be a near-limitless energy source. Space travel. NASA has theorized antimatter-powered spacecraft, but the cost is far too high for practical use. Antimatter has fascinated scientists and science fiction writers alike for decades. Here's a deeper dive into its discovery, mysteries, and potential future. The discovery of antimatter. The story of antimatter begins in 1928, when physicist Paul Dirac was developing equations to describe electrons. His work predicted the existence of a particle identical to the electron but with a positive charge, the positron. In 1932, Carl Anderson discovered positrons in cosmic rays, confirming Dirac's prediction. This discovery won him the Nobel Prize. Later, scientists found antimatter counterparts for protons, antiprotons, and neutrons, antineutrons. This led to the realization that, in theory, entire antimatter atoms could exist. The biggest cosmic mystery: where is all the antimatter? One of the greatest unsolved mysteries in physics is the matter-antimatter asymmetry. According to the Big Bang theory, equal amounts of matter and antimatter should have been created. But if that were the case, they would have annihilated each other, leaving behind nothing but energy. Clearly, that didn't happen, so where did all the antimatter go? Scientists are still searching for answers. Some theories suggest that tiny differences in the behavior of matter and antimatter, called CP violation, might have given matter a slight advantage, leading to the universe we see today. Antimatter in the modern world. Despite its rarity, antimatter has practical uses today. PET scans, positron emission tomography, used in hospitals to detect cancers and brain disorders. Particle research. CERN and other labs study antimatter to understand the universe's fundamental forces. The dream of antimatter power. If we could harness antimatter efficiently, it could be the ultimate energy source. When matter and antimatter collide, they release 100% of their mass as energy, far more efficient than nuclear reactions. For comparison, 1 gram of antimatter equals 43 kilotons of TNT, about 3 Hiroshima bombs. 1 kilogram of antimatter could power the entire world for a day. NASA has considered antimatter-powered spacecraft, which could travel to Mars in weeks instead of months. However, the cost and storage issues make this purely theoretical for now. The dark side. Could antimatter be a weapon? In theory, antimatter bombs would be far more powerful than nuclear weapons because they convert 100% of mass into energy, whereas nuclear bombs only convert a fraction. However, making enough antimatter for a weapon is currently impossible. Even with all of humanity's efforts, we've only produced a few nanograms. Science fiction meets reality. Antimatter often appears in science fiction. Star Trek. The USS Enterprise is powered by matter-antimatter annihilation. Angels and Demons, Dan Brown, features an antimatter bomb, though highly unrealistic. Doctor Who and Marvel movies use antimatter as a futuristic energy source. While today's technology is far from building antimatter reactors or weapons, the dream of harnessing it remains. In a few centuries, antimatter might revolutionize space travel or energy production. Antimatter. The forbidden fuel of the future. Chapter 1. The accident at CERN. In the year 2087, deep beneath the Swiss-French border, the CERN Hyper Collider was running its most ambitious experiment yet, an attempt to create and contain 1 full milligram of antimatter. This was more than humanity had ever produced in its entire history, and if successful, it could revolutionize space travel forever. Dr. Alina Vazquez, the project's lead physicist, watched anxiously as the countdown neared zero. Magnetic fields stabilized. The antimatter chamber hummed with energy. Then, the impossible happened. A sudden power fluctuation caused the containment fields to flicker. The antimatter, suspended in vacuum, began drifting toward the chamber walls. If it touched normal matter, the resulting explosion could level Geneva. Alina screamed, but it was too late. A blinding blue-white light filled the control room. For a brief moment, time itself seemed to freeze. When the light vanished, the lab was still intact. No explosion, no destruction, but something had changed. The antimatter had disappeared, not annihilated, not converted into energy. Just gone. And in its place, a rift shimmered in the air, leading to a place no one had ever seen before. Chapter 2. The Other Side. The rift pulsed with an eerie glow, defying physics as it hovered in the air. It was not a wormhole, not a black hole, something entirely new. Alina's team quickly ran tests. The rift emitted negative energy signatures, something only theorized in quantum mechanics. Then, a voice crackled over the comms. The signal wasn't just random noise, it was a message. A sequence of repeating tones, followed by words. Chapter 3. The warning silence filled the CERN control room as the mysterious message repeated, "You have opened the door. Do not proceed." Dr. Alina Vazquez's heart pounded. "Is this a joke?" she asked, her voice barely above a whisper. But the signal was real. It was coming from inside the rift, a place that, as far as humanity knew, shouldn't exist. Professor Elias Monroe, CERN's top theoretical physicist, adjusted his headset. The communication tech, Raj Patel, hesitated before pressing the intercom. "This is Earth. Who are you?" A low, humming vibration filled the room, setting their teeth on edge. Then, the voice returned, this time, more urgent. "Thanks for watching. Request you to subscribe the channel."